Thanks, Jeff. Okay. All right. So I apologize. My talk title is going to be a bit different to what was advertised. So this is some work that I've done with my grad student Sina, who's at NYU, and also Arthur Schlam, who's a colleague at Facebook Research in New York. Okay. So basically, I'm going to talk about two different things broadly today. So first of all, the first major piece will be really about models that can handle sort of unstructured data, and I'll just explain that in just a second. And there are two papers I'm going to talk about, which are sort of different sort of ways of thinking about tackling the problem. And then at the end, I'm just going to talk about, if there's time, some sort of ongoing work on hierarchical reinforcement learning, which we're sort of looking into at the moment. Okay, so just to motivate, the major part of the talk. So we have pretty good models for certain types of data. So if you have a sort of temporal sequence, things like an RNN, a recurrent neural net, make a lot of sense. If you've got data on a sort of regular lattice, then a convolutional network makes a lot of sense too. But there's a lot of different types of data which don't have that kind of regularity, and we want to be able to deal with deep learning methods. Okay, so you might want, for example, the data might have long-term dependencies that might be hard to capture with a recurrent net. You might have a set of items which have no natural ordering to them, so it seems weird to put them in some sort of fixed temporal order. You might have situations where the size of the inputs is sort of changing dynamically through time and stuff like that. Okay, and the existing sort of architectures that we have just don't sort of address those kind of situations very well. So just to give you a couple of sort of practical examples to kind of motivate these things. So say you're doing a little question and answering task. You're given a little story, a bunch of sentences, and then at the end you have a question, and the network needs to sort of ingest that passage of text and the question and give the answer to the question. Okay, so the thing is, to answer that little question, you actually have to sort of jump around over that passage of text. Okay, so you notice that you need to sort of find something to do with the apple. So that's perhaps the last sentence, and then you need to sort of realize that Sam has something to do with that apple. And that means going all the way back to the beginning, and then subsequently coming forward to something in the middle. Okay, and then based on that final sort of sentence, then you can actually answer the question successfully, okay? But the key point is there, you have to sort of an out-of-order kind of access of the data, which, in theory you could do with an RNN, but as we'll see, in practice, they don't do as well for these kinds of things as the models that I'm going to talk about. So a second sort of motivating example I'll show you is, where's my video? Does this play? Okay, so this is a little example of, controlling cars. Each little car here we're going to control with a little neural net, and they have to sort of learn to basically avoid colliding into one another when they go through this junction. Okay, and the difficulty is that the number of cars is changing dynamically and stuff like that through time. So it's not obvious how you would apply a standard model. Yep. Sure. Yep. Where did Sam come from? I think it's where was the apple after the kitchen?
But there seems to refer to where Mary left the milk.
Sometimes the apple, the kitchen. The kitchen, I believe, is the thing, right? So, but some of the sentences are sort of irrelevant, things designed to sort of, be out, noise in some sense. That's correct. So they're sort of disjoint things, right? So in this case, the fact that Sam has, yeah, something like that. Yes, exactly. This is an artificial data set which people use quite a bit just to sort of understand these kind of reasoning problems. Okay, so the two things I'm going to talk about differ in a fundamental way. So one of them is essentially a serial approach to the problem, where we're going to sort of basically have a sort of form of external memory that we connect to a standard neural net, and we'll have a sort of serial access pattern to that memory. And the second thing I'm going to talk about is a sort of a kind of more sort of parallel approach where everything's sort of done at once. Okay, so it's a little bit. I guess I'll come back and once I've explained the approaches, this in a bit more detail. Okay, so let's just start with this thing called the end-to-end memory network. All right, so just to give an overview of this, so the input's going to be a set of vectors. So each data point will be represented by a vector, and we're actually going to end up learning what that vector should be. So we'll learn some sort of embedding for each data point. We're going to have those vectors be stored in some external memory module, and that will be separate from a little neural network controller. Okay, and that controller is going to perform a bunch of sort of memory, accesses into this external module, okay? So you can think of it as just a sort of read-only memory. You're going to have an addressing operation, which will sort of look up things in the memory, and then a reading operation where you read back from that external memory into the controller to sort of update its state. And there's sort of two sort of key points, I suppose, here is that this memory is going to be, it's not a discrete memory like you have in a computer. It's going to be a sort of a soft thing, so it'll be sort of continuous, this both the reading and the writing from the memory. And that's very useful because then when we have many memory accesses, we can still backprop through all of them, okay? So this is what gives rise to the name end-to-end, because we can now train the whole model to sort of learn the right memory access patterns such that we give the correct answer to for example, the question at hand, if we're doing that kind of question and answering problem rather. Okay, so just to explain this with a picture. So here we go. We've got two separate pieces to the model. Okay, we have a controller on the right side, a memory module on the left. The memory takes as input these memory vectors, M1 through Mn, which will be learned. So there's no ordering to these. They're just a set. And then you have some initial state for the controller. Okay, and that will depend a little bit on what the application is. And then what will happen is you'll have this addressing operation where you use the vector of the controller state to kind of access different elements in the memory, and then you're going to read back some vector from memory. So I'll explain exactly how these two operations work in just a second, and that will update. You'll add back the vector you read back from memory to the current controller state to produce U2. Okay, and then you can repeat this operation, a fixed number of times. You have to decide how many of these sort of hops, as we call them, you're going to do, and then you will produce, from that controller state, you'll then have some discrete output over, say, vocabulary or something like that. And the idea is you're going to have supervision at the output, and that's the only place you'll have supervision. Then you'll sort of backprop through all the arrows you see on the diagram to sort of learn the weights in the controller, so the controller parameters, and also the memory vectors in the memory at the bottom. Okay. So just to look at how the memory module, just a second. So just to contrast this with something like an RNN. So an RNN effectively is what we're going to be using for the controller. So an RNN, it is capable of memorizing things, but it has to do it sort of in its hidden state. Okay, and in this case, the difficulty is that the hidden state sort of evolves over time, and it's hard to keep things, remember things in the hidden state for long time intervals. Okay, so you see lots of adaptations of RNNs. Things like LSTMs and so on, where they have some sort of gating of the hidden state. So in this case, you don't need to do any of that because the sort of set of inputs are just sort of fixed. They're just sitting there, and then the controller can just access them as and when it pleases. Okay, there's no need to sort of store them internally within the model. In this particular incarnation, yes, that's right. Okay, so just to look at how the memory module itself works. So you have a bunch of memory vectors. You have this addressing signal, which is going to be a vector of the hidden state. From your controller. And then basically all you're going to do is a dot product. Okay, so you do that on each of the memory vectors, you get a series of scalars, and then you're going to pass them through a softmax. And so now you have a sort of normalized vector, and you can think of this really as an attention over the different elements of the memory. So this is the soft addressing operation, if you like. So if in a hard addressing operation, you have a single one in one location of that vector. But in this case, because it's we have a dot products and softmaxes, it'll be soft numbers. Okay, so 0.5, 0.2, and so on. So you can have the attention spread over multiple memory elements. And that's the addressing phase. And then the reading phase just takes that probability vector, so those are essentially weights over the different memory vectors, and then does a weighted sum over them. Okay, so the output will be a sort of weighted combination of the elements you have in memory. And that will then just be, you take that weighted sum, you'll add that to the control state, and that's sort of, the end of one hop, as it were. And so I'm just going to explain now for a moment where we would get these memory vectors from. Okay, so the basic idea is, at least for the problems I'll show initially, where we have things like, those little sentences, we're doing a question and answering problem. The basic idea is we would have an embedding vector for each word, which we're going to end up learning. And then to represent each sentence, we will just do a sum of the embedding vectors. So it's kind of like a bag of words representation. Okay? So each word there has its own vector in some high-dimensional space, say, 30 dimensions or something. And then you just add those vectors together to get a final sort of representation of that sentence. Now, in some cases, you do want to, encode some kind of structure. So say, in some of the situations, we'll see that you do perhaps care about the temporal ordering in which things occurred. In that case, you can simply add a kind of a word that corresponds to some sort of time index, okay? And then you don't need to, you can just learn that as well. You don't need to sort of hand specify that. But that would be a sort of an extra signal that you put into the representation. In this particular example, yes. But we'll look at examples where they would be, you can have different things as the memory vectors. Okay, so the key point is there that, for the time index is just represented by another vector. Okay, so just to see how it's going to work then for that little question and answering problem. So each of those sentences in the story will get represented as a memory vector. You'll have the question will now be, you'll have the same bag of words embedding we use for the sentences in the story will be used for the question. So that will produce the initial state of the controller, and then you're going to have that dot product of softmax get some kind of weighting over the memory elements, and then you're going to have a weighted sum now coming back into the controller over those memory vectors. And then in this case here, we know the answer is kitchen, so you would be able to backprop through this model to learn the move around those embedding vectors, move around the memory vectors, such that it produces the correct answer when you do this thing. There's also, of course, the parameters in the controller that evolve the state there as well that will be learned. Okay, so just to compare this to like an RNN, which many of you may be familiar with. So an RNN, of course, is a recurrent model where you propagate state. But what's happening, of course, is that you have a sort of different input at each step, as it were. So the recurrence is kind of over inputs that you would use. So in this model I've described, this memory network thing, you basically would have a single sort of input, and then you do have recurrence now, but it's really over these memory accesses. Okay, so you can think about you have some initial embedding, and then you have this memory lookup, and then that's then used to sort of produce, index the next thing into memory, and so on. Okay, so that and then you would have a final output. So instead of having multiple sort of inputs here, you've just got a single input and a single output. Okay, so just to sort of now talk about related models. So the thing I'm describing here really is a kind of is builds directly off this original idea of a memory network that was introduced by some of our colleagues at Facebook in New York, so Jason Weston and colleagues. So this essentially the initial version of this model just used a hard addressing operation. Okay, so instead of having a soft weighting, they basically had hard attention. So you just pick a single memory vector to access at each time step. Now the problem with this is you can't backprop. Okay, so it means at training time you actually have to supervise. You have to say which was the relevant memory that you should be using at each memory lookup. And that's, in toy problems you can do that, but in real problems it's actually very unclear what the model should be using. And so this is fine, but it's very restrictive in some sense. To the kind of data we can apply to this model. And then, of course, there's been a lot of work recently on using attention in a variety of settings. So that you can think of our model really as a kind of multi-stage attention mechanism over this sort of fixed set of inputs. And if you think of things like machine translation, so from Joshua's group in Montreal, so they've got a sort of encoder-decoder structure with an attention mechanism that kind of can focus on different parts of the input sentence when they're decoding the output. And then that was sort of one very directly relevant thing. And then there's a whole bunch of people recently thinking about how to add sort of external memory to neural nets. So for example, Thomas Mikloff and Armand Julin at Facebook, they have a sort of formal, a sort of stack, like a sort of computer science stack which you can push and pull to. Pop the stack and push to the stack, and that's controlled by an RNN. And then the folks at DeepMind have things like the neural Turing machine, where you have, again, a sort of differentiable form of memory, random access memory that can be used. And it's actually, I think a lot of these, to be honest, this idea of having an external memory goes back a long way, right? There are people, from a long time ago who thought about these things, and I guess these are just, the models we're talking about here are kind of modern versions that have the benefit of being able to be, you can actually build these models and train them on decent-sized data sets. And then I guess, there's been a whole bunch of people applying, attention in different settings. So there's a whole bunch of papers in the last year or two, applying this general concept of attention over your input in a bunch of ways. Okay, so just to show you some results. So this was the example I gave earlier was actually a little one particular example problem from a suite of tasks called the bAbl. So these are a series of sort of artificial little question and answering problems. The idea is that you have to read some short story and then answer a question. They deliberately simplified the language, so you're not sort of struggling with kind of synonyms and things like that. And the idea is that each of those 20 tasks requires a different type of reasoning. Okay, so you can see that one on the right requires some sort of logical induction thing. The ones on the left are sort of, multiple sort of stages of just remembering things. And because they're synthetically generated, they can generate sort of a large quantity of them. So there's a sort of 1K version, there's two versions of the data set, which has one of them has 1,000 training examples, the other one 10,000 for each task. Okay, and so what we can do is we can basically train up the memory network model on this data. Okay, so this is just to sort of show the evaluation here. So this was the hard attention version of the memory network, where you have to supervise the memory access at each time step, which is basically effectively saying, in the passage of text, which sentence should I be looking at each memory access? Okay, so that's obviously a lot of extra information. So in the one I've just presented, we don't have that information. We're not going to use that information. All we're given is basically the answer to the question, shown in red. So in other words, this one gets a lot more information. So this one, in some sense, represents kind of the best we could really probably hope to do. If you train an LSTM on these things without, this is again all the ones below the dashed line to just get the answer as their supervision, you can see that they fail on most of the tasks. So out of 20 tasks, even with a lot of training data, it's only really succeeding at 4 of them out of 20. If you use the sort of the simple representation for each sentence, bag of words, you can see you actually start to begin to solve some of them. And if you add a few tricks in, essentially to the representation you use for each sentence, then you can actually start doing pretty well, and so on. So solving a task means getting less than sort of, I think, 1% error or less than 0.5% error or something on it. And just to look at this in a slightly different way, this is just showing the sort of refinements you can make to the representation you use for each sentence. This is just bag of words. If you introduce some sort of position encoding that tells you where the sentence is in the passage of text, that helps. And there's a few things to do here with the training that can also help as well. And you can see that all these little tricks, generally sort of help reduce the average error across the different the set of 20 tasks. And clearly, having more training data really helps, so that the 10K error is much lower than the 1K error. And then what you also see, of course, is that having more chances to access the memory helps too. So we see that some of the problems you can't solve unless you have 2 or 3 memory accesses. So unsurprisingly, the sort of average error rate drops when we allow the model to use 2 or 3. We did try more than this, but it doesn't actually make any difference to performance. And there remain 3 tasks here that stubbornly can't be solved very easily. I should say that there's been quite a lot of work on this whole benchmark recently. So Jan and others at Facebook, in fact, and Arthur Schlam, who was involved with this work, they have a model which just recently can actually solve all 20 of them. But there's been a whole bunch of people sort of hammering away trying to get a single model that can handle all 20 tasks. Oh yeah, I should make clear, by the way, this is the same model, right? So we're not training a separate model for each of the 20 tasks, right? The model has to generalize to the 20 different problems. Okay, so just to show you some examples of how the memory is actually working. So this is, this is the sort of basic induction type problem, task 16. So the question is, what color is Greg? Okay, this is what we're looking at in this column is the sort of weight over the different memory vectors at each memory access, each hop. So what you see here is that in the initial first hop, in the first hop, you see that most of the attention is on this last sentence, which is, because the word Greg appears here, which is also in the question. And then, of course, the other part of the sentence is frog. And then what you see now is that the next memory hop, the attention is pretty much on that first sentence, which is saying Brian is a frog. And then it makes the link to Brian is yellow. And then the output here is yellow, which happens to be correct. Okay, so these are just a couple of examples of the attention. All right, so that's one sort of application. So you can take the same model and you can apply it to other problems. So one of them will be something like language modeling. So in this case, your task is you're given a sequence of words, and you need to predict the next one. Okay, so Jeff says your model must be, and then what's the next word? So it might be something like deep, for example, if you know Jeff. And so the idea is here that we're going to now, instead of embedding each sentence with a single vector, we're going to just embed each word. And we will have some sort of positional encoding too, so that it knows the order in which the words are coming. And then this will be a little RNN, and we will see how well we can predict the next word. Okay, so this is a kind of a problem that a lot of people work on, and it's, if you can build good language models, you can use that for all kinds of things in natural language processing and speech. So we tried two different data sets here, PenTreeBank and Wikipedia. And the metric they use is complexity. You can roughly think about this as this is the uncertainty essentially of what the next word will be. So this is roughly a measure of the size of the vocabulary. So if it was a perfect model, you'd have perplexity 1 because you would be certain what the next word is. But this is just giving you some. So you can see this is on this data. It's still quite a lot, relatively high perplexity. And what we've done here is to sort of have as a baseline an LSTM with the same number of parameters. Okay, so this is a kind of an equivalent model essentially to the memory network that we're trying to train up. And we can see here, as we increase the number of memory hops, the performance improves, and it does sort of comparably well, basically, to the LSTM on both data sets. And you can also try a few things like increasing the window size of the model. So this is just the history it keeps around, and you can see that with the memory network, it tends to sort of roughly improve things as you make the memory bigger. So anyway, bottom line is, the same sort of architecture you can use for language modeling, and it seems to work at least as well as an LSTM, rather. I should say these numbers, by the way, are quite a long way off the state of the art. The reason is that, our model is pretty small in terms of number of parameters, and therefore the LSTM we're sort of comparing to here is also much, much smaller than the big ones that you have at sort of Google and other companies, which, are trained on ginormous corpora and stuff. So if you look, you can look and go in and visualize the attention over the previous words in the sequence. So initially, what you see is that each row is a different memory access, and the white indicates sort of which words it is attending to. So the most recent word's on the right, and the most oldest one is 100 words previously on the left. And you can see it has this funny pattern it's learned, where it kind of looks at the previous word, and then it goes back and looks at sort of it's averaging out here over the context, over the previous, the entire sequence basically, or not the entire sequence, sorry, the entire window rather of 100 words. And then once it's got that sort of global context, it comes back and does a sort of, more local attention again, and then goes back and does another attention over, many of the previous words, and then comes back and so it seems to alternate between kind of doing a sort of, just looking at sort of the local context and looking at the more sort of global context. Okay, so you can take, this basic idea of attention you can actually apply very easily just to sort of, for writing as well to memory. So I'm not going to go into that too much here. You can get it to do simple things like sort numbers and stuff like that. This is actually, in this form, it's actually very, very similar to the neural Turing machine, which used this kind of thing. So this is they had more bells and whistles and stuff like that, which makes their thing a little bit more complicated. But in principle, you can also use attention to sort of write vectors to memory too. All you need to do here is just, again, sort of provide supervision as output. So in this case here, you can actually have output sets, for example. Your input would be a set of unsorted numbers, and the output could be a set of sorted numbers. Okay, so just to sort of summarize this little part. So basically what you have is a little neural net controller. It could be an RNN or an LSTM, whatever you prefer, really. And your data is sort of preloaded into this external memory, and you can access it in arbitrary order. And it's kind of a serial access over time, and you can train this thing end-to-end with just standard backprop. Okay, and so you can apply these models to, we use them for reinforcement learning, for playing little silly games, things like that. And if you want to try out, and you saw also them being applied here to things in sort of question answering and language modeling and stuff like that. Okay, so if you're interested in trying it, there's code available online in both MATLAB, I think, and Torch as well. Okay, so what I'm going to talk about next is this thing called a communication neural net. All right, and so this one is a slightly different paradigm. So each data point, again, it's going to be, just a set of data points were given. Now, this time, each data point is going to have its own little processing stream. And what we're going to provide between these streams is a communication channel. And it's going to be a sort of broadcast channel. So that, in other words, they all get to sort of shout together onto this channel, and then they hear what everyone else is saying. And that's all we're going to specify. And what the models then, what each stream has to do is to sort of learn to communicate. It has to learn a protocol to communicate to its neighbors, essentially, to solve the task. Okay, so this is a paper we had just at NIPS this year, again with Sina and Arthur. So just to show you, this is really the nitty-gritty of it. So essentially, each data point is going to be, sorry, where's my mouse cursor? Here we go. So I've lost the thing. There we go. Okay, so each data point is going to have its own stream. So each data point will be presented. We'll have some embedding function for each data point, which will come in here. So if we had 4 elements in the set, we have 4 streams, as we show here. And what's going to happen is that each input embedding will be passed through a little module, and each of these little green boxes is going to be a neural net. So you can think about this as just, it could be a single layer neural net, it could be just a multi-layer perceptron. It doesn't really matter. And what's going to happen then is that there will be sort of a sequence of communication hops between these different streams. Okay, so in this case, this little figure, we're showing 2 of them. So in each hop, what will happen is that the hidden state of each module will be just propagated forward up to the same module just now, 1 hop further on. But we're also going to propagate the hidden state onto this communication channel where the hidden state of all the agents will be summed and then distributed back to the streams at the next hop up. Okay, so very roughly, this is just looking at the sort of input-output for each module. So if you take, it's going to have an input, which is the hidden state of the module in the same stream at the previous hop, so from down here, and it will also receive this communication vector. Okay, now what this is basically going to be is a sum of all the other streams. So, for example, if we take the first one here, this would be over 2, 3, and 4, and then we're going to average over the number of streams. Okay, so you can see that if we vary the number of streams, then the overall sort of magnitude of this signal isn't going to change. And so then these will be the 2 inputs to the module, and then the output would just be an updated hidden state, and that will then be pushed onto the broadcast channel for the next communication cycle. Okay, so the nice thing about this is, so it's a very, very simple communication setup. It's about the dumbest one you could think of, possibly. And the advantage of just using a summation is that we can sort of backprop through it. So we can train this whole thing with backprops. The idea is that this will produce a series of outputs for each stream, and then we'll have some kind of supervision at the top here, which we can then use to essentially, just backprop everything through and update what's going on inside these modules. Okay. Now, what we're going to do is actually the parameters across each of the streams will be tied at a given hop. So all the same things of the same color will share parameters. Okay. But we will have different parameters at different hops in the model. And then the other important thing is that because you have this averaging here of the hidden states on the communication channel, we're invariant to the number of inputs. So if the number of streams changes over time, it won't break things. And as we'll see, the model can handle that thing just fine. And the final point to make is, because you're just doing a summation here, it doesn't matter, there's no inherent ordering to the streams. Okay, so you can just permute the streams. It wouldn't make any difference to the model at all. Okay, so we do have, just like in the end-to-end memory network, we do have a fixed number of hops. In this case, it's communication hop rather than a memory access. Okay, so that's decided beforehand. Okay, now you can actually think of this actually as just one big model. Okay, so if you just, as I said, remember that you can think of we tie parameters across within a given hop. Sorry, here we go, the mouse cursor. Within within one hop, you share the parameters across the different streams. Okay, so what we see here is to compute the hidden state. You've got this is just showing how the new hidden state is computed. You'll have a matrix A, which will essentially which will act on the hidden state from the previous hop, and then you also have a matrix B, which will act on the a vector from the communication channel. Okay, and then you pass through some nonlinearity to update the hidden state. Now you can rewrite this whole thing actually as just one big block matrix. Okay, so the basic idea is that you can see the superscript I here is because if you have I is the hop index. Okay, so at communication hop I, you can rewrite the whole sort of operation here as just one big matrix T, where the diagonal now is a series of these matrices A, and then off diagonal you have this B, which is basically this broadcast communication. And so this matrix, of course, if you're changing the number of streams, the size of this matrix will change over time. And the modules here are sort of connected essentially by type. The index is sort of the index of the ordering of them is kind of irrelevant. Okay, so we didn't actually go into this, but you could easily just have multiple types of stream. In this case, the only type, I suppose, that really is that you have the same, modules connecting to themselves at the next hop or to different ones.
Does every example have a different number of streams?
Each example gets one stream. So each example is a column in this. Each input data point is a column in this diagram. Yeah. Okay, so just to contrast it with the memory network model. Okay, so in that one, you had this sort of sequential access here of the memory to sort of figure out what the answer should be. In this one, there's a sort of distributed operation. There's no central controller. All the agents, sorry, I keep saying agents, as you'll see in a moment. All the different streams, rather, have to just chat with one another to sort of figure out what the right answer should be. Okay? So just to illustrate a little how you would apply this, for example, to those bAbl tasks, what you can now do is you can treat each sentence as, give it its own stream. So you'll have an embedding for each sentence, which will be this sort of bag of words representation we saw before. And effectively what's going to happen in this model is the sentences is going to chat to one another to figure out, what the answer should be. And of course, need to know what the question is first. So we also have to provide the question as an input to each of the streams as well. Okay. Now in this particular task, we don't have a separate output for each sentence. We have a sort of single one. So we just simply add the vectors at the output and push it through a softmax. Okay. And then we have supervision at the top saying it's a kitchen. And so you can actually train this model to do the bAbl tasks. And you can see this is just comparing to some of the other methods. So you can see it doesn't do quite as well as the end-to-end memory network. This is just a little histogram of the errors. So there's a couple of tasks where, for whatever reason, this particular communication thing doesn't work very well, whereas the end-to-end memory network did okay. So and so you can see that it is definitely using communication. So if we turn off the communication, if we just sort of propagate the hidden state from hop to hop, then the error rate goes up, and the number of tasks it fails at goes up as well. Okay, so I should point out, yes, there are. I mean, the state of the art on this is actually it's better. So yeah, the recent paper from Jan and Arthur Schlam, this entity network idea, actually solves all of them. So it doesn't fail in any tasks. But anyway, this is other more recent work since we published the memory network stuff. So another little example of something you can do, just to illustrate sort of how you can act on sequences, sets of words. So you can actually just give it a set of words. In this case, is mouse cat chasing, and the objective here is to output the words sorted into sort of the correct order. Okay, so you have to basically now, you're given these n-grams, and you have to, unscramble them and turn them back into actual sentences. Okay, so this was just a little experiment we did where so each word here will have a different stream, and essentially the output of each stream will be, the target for each stream will be essentially the correct position of that word. And we use 2 hops trained on GigaWord. So this is for 5 grams, and each module is just a 2-layer multilayer perceptron. And you can see actually that you can do pretty well. I mean, this was some kind of language model. So the naive way to do it would be to use some language model to score all the different permutations of the words and pick the one with the highest likelihood under the language model. So if you do that, it actually turns out to be a surprisingly hard thing to do. And this model seems okay at doing it. Now, one very natural setting for this actually is in reinforcement learning. Okay, so instead of you can now think of each stream basically as corresponding to a single agent, and the input to each stream will be the world state of each agent sees, and that will be sort of embedded in some way, so it'll be a continuous vector, and then your output will be an action, a discrete action that you take for that agent at that particular time step. Okay, so the idea is that the agents are going to sort of chat amongst themselves to figure out what to do, and in this case, we're solely thinking about sort of collaborative tasks, where so the reward that we get, so this is, you can think of this as a sort of inner loop, basically, and around this whole thing, we'll have a sort of standard reinforcement learning algorithm, say like, policy gradient or something, okay? And at least in this situation, we're considering scenarios where the reward that you get from the environment is going to be shared equally amongst all the agents, okay? So you can only really, in that setting, apply it to sort of collaborative tasks, where all the agents are kind of chatting amongst themselves to figure out how to sort of maximize their kind of collective reward. Okay, so one little example is that the road junction thing I showed you earlier. So the idea is you have cars coming to a four-way junction. They're on fixed routes. They can only go stop, or they can go forward one square at each time step, and they're driving in the fog. Okay, so because they have limited visibility, they're going to smash into one another, with fairly high probability, unless they sort of learn to chat with one another to sort of come up with a way to sort of avoid colliding. Okay, and there'll be a sort of heavy penalty for crashing into one another, and we also have a little small penalty for sort of, at each time step, just so the cars want to get through the junction fast rather than hanging around. So in this, so what we're going to do is actually vary the amount of visibility that each agent has, and the number of cars on the road at any time will actually vary as well. So that sort of places this notion of having sort of dynamically varying input size the model has to deal with. Okay, so this is, I'll just show you initially what happens when the model's initialized randomly. So of course, and this is zero visibility. So they're driving, all they can see is themselves, they can't see anything else, but they can talk to everybody else over this communication channel. So initially, it's just demolition derby on the road, okay? All the cars are smashing into each other. You can see the number of collisions at the bottom right. So when you see the XX, that means they've just smashed into one another. So it's complete chaos. Okay, now after, running the reinforcement learning for a bit, and they basically have to learn to communicate amongst themselves, suddenly it's, super efficient, and they're just zooming through. When you see that the inverted symbol, that's when they're braking, okay? They're putting on the brake to avoid crashing into another car. And then you can also apply it to sort of, even slightly, bigger scenarios. So this is, again, sort of Manhattan. We have four-way, 4x4, so four-way junctions. And, this is, before training, so it's obviously, bad news for the drivers. And then afterwards, it runs very smoothly. Okay, so just to sort of quantify that, just to show you some graphs. So what we're doing here is varying the visibility on the x-axis rather. So obviously, the less visibility there is, the more it has to rely on this communication channel to be able to, achieve the task. Okay, and then what we're measuring here is sort of failure rate, which is if there's a single collision during an episode of, some fairly long time interval. And what we're seeing here is if you don't have any communication, then if you can't see where you're going, then sure enough you're going to have lots of collisions. But if you engage this, if you allow the agents to communicate, then they can actually start to do okay, and they will succeed in a fair number of instances. And of course, adding in some visibility to the environment will help too. We did try discrete communication. So in this example, the communication vectors are continuous things. We did try quantizing them to be basically discrete outputs. Think as if we had a fixed vocabulary. But that actually seemed to sort of break things. I mean, it just never worked as well as letting things be continuous. And so we also tried playing around here with a bunch of sort of baselines. We tried, you can try different models for the modules. So multi-perceptron, you can have an RNN or OSTM. It doesn't make a huge, it makes some difference, but the overall story is the same, that, having some communication helps. You can also try, as I showed previously, you can think of this as just one big model. You could just do away with the architecture that we impose here of having this sort of fixed communication channel. You could just give it just one massive multi-layer perceptron to control all the agents. That's what this dense thing is effectively. But you can see that doesn't do as well. Okay, so that doesn't do as, this is failure rate, so lower is better. You want, this is 2%, this is 12%. Yeah, I'll just skip over these numbers. We don't need those. So the question is, how is it solving the problem? So what we did is we went in and just recorded the communication vectors that the agents were sending to one another over the channel, for several episodes, and we went and did PCA on them down to 2 dimensions, and then plotted them out. And what you see is quite interesting, I think. So this is just the first 2 principal components. And what you see is that, first of all, quite a lot of the vectors sort of fairly near the origin, but you see then these sort of clusters of vectors that seem to be, relatively high energy that is distinct from this sort of lump in the middle. Okay, so the question that the natural instinct might be, well, okay, you look at this lump and you might say, well, maybe some of the agents are just sort of not doing anything. Maybe they're just turning off and just following some sort of very default policy. So what you can do is you can look at the hidden state that corresponds to that the particular agent that sent that communication vector. So this is where we're using the color coding. So this other diagram, I'm just plotting out the sort of doing PCA on the corresponding hidden vectors for each agent. So if the agent had died and was really not doing anything, you would expect to see basically all these guys, all the green ones, be near the origin as well. But what you see, that's not the case. There actually definitely is information carried in the hidden state of each agent. But what's effectively happening, though, is the agents are learning to be quiet. Okay, so the problem with that broadcast channel, because you're averaging over all the other agents, is that if everybody says something, then no one can hear anything. Okay, so what's happening is that most of the time they're staying quiet, but occasionally they actually say something. Okay, and then these obviously are sort of somewhat akin to kind of words in the sense that they're sort of discrete clusters. And what you can then do is probe some of these and find out, what does this actually correspond to? So what we did was to look at the behavior of the agents, when somebody uttered, this particular communication vector. And so, for example, that cluster A seems to correspond to when you have an agent that comes in. Sorry, where's my mouse pointer? Sorry, I'm struggling with there we go. So when the agent comes into this position on the road here, we found that when it then utters that vector from cluster A, and what that causes other agents at these positions on the road to jam on the brake and stop. In other words, when this guy's coming through the junction, he's like, hey, guys, from the other direction, please stop because you're going to run into me. And similarly, you see these other ones. You see this is one where, for B and C, you see, it's telling vehicles in other positions to stop as well to avoid collisions and so on. So it's learning something reasonably sensible, it seems, which is kind of nice because, obviously we didn't tell it to do this. We just gave it the kind of overall architecture for communicating. So we also then applied it to a couple of other problems. So we tried it for, this is a very simple sort of idealized kind of, StarCraft-like game where you have a bunch of little agents that have to run around and shoot at other agents and try and kill them. So each agent has sort of health and things like this, and they have a certain range they can shoot and this sort of thing. And they have things like cooldowns, so when they shoot their gun, they can't fire immediately afterwards. They have to wait a few seconds. So there's all kinds of, they have to learn sort of tactics, essentially, like sort of ganging up on the weakest enemy bot and stuff like that and so on. So anyway, bottom line is you can, so the blue ones are going to be enemy bots that are they're operating under some kind of simple default policy. Then the red ones are going to be controlled by this communication network model. Okay, so the agents have limited visual range, but they can chat with one another. And what we see is that, you can actually get this is win rate, so higher is better here, so that you do see that if you allow them to communicate, you do get sort of improved win rates. So the win rates are kind of low by default because we give the enemy bots an inherent advantage by giving them full visibility and things like that. So I should say, because this is all reinforcement learning, there is actually a pretty big variance. So what you actually in practice, typically there's a big advantage to having the communication, but occasionally, for whatever reason, the model comes out a complete dud. So that's why you've got this quite big error bars on things. It's really quite a bit bimodal. And then, if you try sort of other baselines, like discrete communication and just having this one big model doesn't seem to work very well. You can play around with things like changing the sort of number of agents. It still works when you have a reasonable number of agents and different visibility levels. And the other fun thing you can do is you can try also sort of hierarchical stuff as well. So you can think about a scenario where, and this is what I've been describing as one where effectively each agent can chat amongst themselves. That's the sort of middle diagram here. But then there's a sort of third scenario you can envisage where you have a kind of general, and the general can't take any actions himself. He can't shoot the enemy, but he has full visibility over the environment, albeit at some sort of low resolution. Otherwise, he'd have too much information if you just gave him the full resolution version. But he can chat. Each of the soldiers, as it were, can chat to the general. So the general can kind of coordinate the troops to go in and shoot at the enemy and stuff like that. And sure enough, you can see that actually, it learns to sort of some communication protocol that lets it win more often than if it didn't have that available. Okay, so just to talk about related work here. So this is the model I've described here. This communication neural net is actually a sort of practical instantiation of graph neural nets. Okay, this idea that you have nodes which correspond in our case to agents, and you have the edges on the graph correspond to sort of little neural network modules. And so I should say this is obviously actually a paper from the Toronto folks, Rich Zemel and others, that came out iClear last year. So this is a sort of a sort of more recent version of them. And so this is basically you can view our thing as just an instantiation of these kinds of models, very much. I guess we're just applying it to some sort of couple of toy problems. And also in the sort of robotics community, there's a whole literature on like multi-agent reinforcement learning. But what you see there is that they actually, they hand specify how the agent should communicate. The agent's allowed to say, communicate their position, or like, when one of them is, shooting their gun or something like that. Okay, but in other words, it's a fixed communication protocol. So I guess ours is different. They were trying to learn it. And there was a NIPS paper this year from DeepMind where they were also trying to learn communication in a multi-agent setting. And this was where they had a pair of agents trying to solve little riddles. Okay, so I guess, our ones, so these were quite interesting little problems. I guess ours is different in the sense of, we're sort of handling, many agents on that 4-row junction thing. We're handling sort of 30, 40 agents or something on the, at any one time. Okay, so just to summarize this, this is essentially it's a kind of distributed neural network model, okay, where, again, you're taking in a set of items as an input, and if needs be, you can also learn the embedding representation for each of them, and then our outputs will be one for each element of the set. Okay, so you have a sort of set of outputs too, and at least for some of the sort of things we tried, it certainly seems to work reasonably well. It looks like it's learning some sort of sensible communication protocol. Okay, so I have about 10 minutes left. I don't know whether I could just stop here and we could ask questions, or I did have a small other section which I probably won't get through in entirety, to be honest, on trying to do hierarchical reinforcement learning. But I don't know what people think I should do. So, okay, you want me to continue? Okay. So I know it's always awkward asking the crowd this. I should just do it. Okay, so I'll talk about this very briefly. This is ongoing work. We still don't have this working on any real data, I should say. So hierarchical reinforcement learning is a sort of vital thing. If you have very complicated problems with huge state spaces, and you might have to take, hundreds or thousands of actions before you get a reward, it's sort of the current sort of reinforcement learning algorithms, which are kind of flat in some sense, just break down. And you really want to try and learn some sort of abstraction that lets you break the big complicated problem into sort of smaller, manageable, potentially reusable pieces. So for example, if you want to get to work, just think how many different individual motor actions you need to take, all right? But in practice, of course, you break it down, like, get out of bed, brush my teeth, get in my car, and so on and so forth, okay? So what we'd like to get to is be able to learn this sort of thing automatically with deep models. And so what we're going to do here is, the key idea is very simple here. So in standard reinforcement learning, you basically have this idea that you have some sort of observation of your state that's plugged into some sort of, policy. So these days, of course, this is a deep net, and that spits out some kind of action or some distribution of actions. And in this case, what we're going to do is just essentially also have some representation of the task as a continuous vector, which will be part of the input now to our deep net, and then we'll have the action will be an output, okay? And so the idea is this task could be the overall problem, like, Rob wants to get to work, or it could be a subtask, like, Rob wants to brush his teeth. Okay, so this is the sort of conceptually how it's going to look. So you have some overall task here, which will, is specified perhaps by in natural language with some sort of embedding of the natural language that you could use to give you a sort of continuous vector. And then this, you have some sort of observation of the world. And then essentially the policy has a couple of options. So it can either output a standard action in the world, like walk left, pick up the object or something. Or it can decide to recurse. Okay, so if it takes that recurse action, it basically clones itself, and now part of that action is to output the subtask vector. Okay, so that subtask vector will now be the sort of input to this policy. Now, in the simplest form, you would this policy will be the same one as the one up here. Okay, so obviously if you have a deep net, you can sort of overload these multiple sort of roles for the policy network into one. And then the same thing can then apply. So this network down here can decide, does it want to recurse or not, or should it take an action in the world, and so on. Okay, so essentially, this is just a pseudocode. Essentially what happens is that you have a kind of augmented set of actions for your agent now, which is either to actually do a regular action in the world, or sort of call itself with the sort of subtask. So there's a bunch of people thinking about how to do hierarchical reinforcement learning is sort of a very hot thing at the moment. There's a bunch of ICLR submissions trying to do this. I think a lot of these ones are giving quite a lot of supervision in some sense to problems where they sort of effectively use supervised training for sort of the subtasks, and then once they've got supervised, once those models are learned, then they learn how to assemble them into more complicated ones. So I guess the difference in our thing is we're trying to learn the whole thing sort of together without explicitly saying what is an atomic subtask and what is a sort of compositional overall task. So at the moment, we just have a sort of simple ID. In these toy examples I'm going to show you, we have a sort of fixed ID for the tasks. I think what we're trying to get to is, of course, where you have actually lists of words, right? So if you have simple sentences like closed door, each word could have an embedding, that kind of thing. It'd be easier to generalize to unseen things. And the idea here is that we're going to have just sort of random. The tasks will be mixed up in a big bag during training. So sometimes the tasks will be something super simple, like just pick up object X. Other ones might be much more complicated, like make coffee. Okay, and that's obviously that make coffee task will be a composition of a bunch of the subtasks, like grasp X, bring X, and stuff like that. Okay, and the basic idea is that during training, initially, the model will, completely fail at these complicated ones, but that's okay. It'll hopefully pick up on these easy ones, like, grasp X and so on. And then later on in training, once it's figured, it'll have reasonable models for these. It can then figure out how to solve these more complicated ones by sort of calling these ones as part of the recursion. That's the idea. Okay, so this is the very simple toy world that we're doing. Basically, the idea is that we're going to the sort of subtasks, the atomic subtasks, like grab these different items, and then you have these sort of more complicated tasks, like make two objects, which requires you to pick up the wood, pick up the iron, move over to the work table, and then this is of course sort of Minecraft motivated, and then you can. And so the idea is you can't really solve these guys until you figure out how to achieve these tasks and so on. And it doesn't know at training time which ones are hard or easy, and we don't specify which. It doesn't know in the make hammer task that it has to do the wood and the rock and go to the tool shed. Okay, it has to figure that out for itself. So this is basically our policy is a little neural net with two hidden layers. Things trained to reinforce. We have a little penalty to make the thing go fast. Okay, and then we do have some slight incentive to use recursion that increases with time. Okay, so basically the idea is that this is just showing success rate as a function of training. So it picks up the easy tasks sooner, and then once it's got those, you can see that it starts to now make progress on those more complicated ones you see in green. And then you can see this is just showing how it uses recursion. So initially, it figures out for the easy ones it doesn't need to use recursion. And then for the more complicated ones, it realizes, okay, yeah, maybe I actually do need to use recursion, and ends up using it. And just to show you, if you don't have the recursion, you can't really succeed on these tasks. The model is, at least at this capacity, is not able to succeed without recursing and sort of having its different levels. So here's a little fun video just to end with that shows the thing in action. So this is the little key. So these are the different fabrication tasks it has to achieve. This is the, let me get this right. So this is the current task on the stack. So when you see it recurse, you'll see this thing change up here, okay? So if I can remember how this video works. So, okay, hold on. So let me just, so that's the overall task. And then this thing down here is the current subtask. Okay, so this is make the axe. Sorry, the graphics are messed up. This is the task here is to make the axe, and so to do that, it had to pick up the stone, which is done, I think. And now its subtask is to pick up the wood, which is what it's trying to execute now. Okay, so it picks up the wood, and then it has to go to the tool shed or whatever the heck the thing was. Okay, so anyway, so obviously this is super simple stuff. We'd really like to get this thing working on much more complicated things. And of course, the thing you also want to do is you want to be able to sort of train on this kind of thing and then show it at test time a sort of new compositional task it's not seen before. And it should be able to, if it's got the subtasks down, it should be able to pick up on that new composite task very easily, okay? Because it doesn't need to search in the sort of space of actions. It just needs to search in the space of subtasks, which is obviously a much sort of, much smaller space to search in. So to achieve things. So that's the sort of gist of where we're trying to go. Yeah, we're not quite there yet, as you can see. So, okay, I'll stop there and you can ask me questions about the whole thing. Sure. I don't know how to answer the questions like that. I'll defer it to these sort of people who think about big things like Jan and Jeff and stuff like that. I mean, it depends what you mean, right? I mean, you can, replicate a human's input-output function or something. I mean, I don't know, maybe enough people. I have no idea, to be honest. Sorry. Yeah. Sure.
Yeah, I just wondering if you can comment on any password relationship between the memory set and the
Oh, right. So, well, the memory size really in the memory network thing is to do with the sort of number of inputs you have, right? And then the number of hops is, well, how many sort of memory accesses do you think you would need to solve the problem? So, beyond a certain number, it gets hard to backprop through. But, on the language modeling stuff, we did certainly up to like 10 or something like that without too much difficulty. But the two things are somewhat independent from one another, right? So, yeah, I mean, it's what, if you have complicated problems, you will need to have more memory accesses, right? But you could, I mean, you could have a lot of data which goes into your memory, but only a very small set of it is actually relevant, for example. So in those stories, for example, there were a lot of irrelevant sentences as distractors, and I mean, the sentences there were probably, I've forgotten what the exact window size was for bAbl, but in the language modeling, it was like you can see it was 100 or so on the memory size. But, I mean, there's been a bunch of work in this area. So people are now looking at like hierarchical representations for the memory. So obviously computation is a little bit expensive because you have to do this inner product between your state vector of your controller and each memory vector. Okay, so that's if you've got the entire Wikipedia in memory, that's pretty expensive. So you want some sort of, first of all, fast, dot product operation. So if you use some sort of compact binary code, that would make that fast, or some sort of hierarchical organization of the memory, so you don't have to sort of do every element of the memory with at every hop, as it were. Sorry. Oh yeah. Right. It's something to do with the training, right? Because at this point you also have to sort of use reinforcement to sort of figure out what your which word you should utter at each time step should be as well. So I'm suspecting it's more a function of the sort of training. It's just when everything's continuous, it's just easier to sort of train the whole model because you can just, backpropagation tends to work better generally than, your standard reinforcement or anything. Well, I mean, when we did the discrete thing, we just simply gave it, we had a softmax basically that was for the output at each, the output of each agent. So it was a sort of architectural change. It wasn't actually direct quantization to the thing. I mean, it's curious that you see this sort of soft quantization of the continuous communication vectors, and I think that's because effectively when you have noise on the channel, to be overheard over the noise, you have to sort of say something distinct, right? So that's you see that sort of rising naturally, which I think is kind of cool. Yep.
You tried both sum and average on the communication vectors?
Yes, we did. So right. So if you do sum, then it breaks when you change the number of agents. Yeah. So the average thing is important for that. Yeah. Yeah.
For the communication scheme, if I understand correctly, the different screens or agents all have the same weights.
Yes, that's correct.
And it seems like that would mean that an agent only gets to see some sort of combined sort of average of the other agents rather than able to see things that individual agents said, right?
Well, that's basically.
There's no way of breaking the symmetry there.
That's right. That's right.
I think it might be more powerful if somehow each agent can have its own little area of communication channel.
Right. So each agent knows who he is, right? So he can potentially put that into the message he sends onto the channel, right? So, right. I mean, yeah. So this I mean, it's a reasonably high-dimensional space, right? So there's quite a lot of potential, stuff that can be put on there. Right. I mean.
So each agent has like an ID number.
Yeah. So it does. Yes. Yep.
So you said that there's no noise in communication, is there? So the actual.
There's. I mean, not that we inject deliberately. So. Yeah. We were wondering about sort of playing around, trying. I think it's one of the experiments we just didn't quite get to. Yeah, I mean, it would be a natural thing to try. I mean, because it might, help a little bit. You can imagine, it would help generalize and stuff like that too. Yeah, I mean, sure.
You started out with NLP problems.
Yep.
It started to say the last 2 years, there's deep learning has had an impact on Facebook scale. You also see that in applications. Is there a lot more deep learning being applied in NLP problems?
Definitely. So they keep me quite a long way from the products, I can tell you. So, and I'm also not really an NLP person, so I have a limited understanding of what exactly is used. But certainly, yes. I mean, the things like translation and stuff like that. All the big internet companies are using deep methods now, I think. I mean, I don't obviously know exactly what their companies are doing, but I think one of the attractions is the fact that you can do things which are convenient, like you can have these common you can have you can train a unified model that can translate between a whole bunch of different language pairs. You don't have to have separate models, and then the fact that they can deploy at scale fairly easily, I think, is in an industry very important, and that ends up being a key factor often. So yeah, I unfortunately don't know too much. I'm not trying to be secretive and things. I generally don't know too much what Facebook does on this thing. So.